So our second speaker, Albert Redo-Sanchez, he is currently a research specialist in the camera culture group at the MIT Media Lab. Albert's background is in Terahertz systems and applications in non-destructive testing and spectroscopy. He built Terahertz systems for the inspection of the insulating foam of the Space Shuttle and studied the application of terahertz imaging to check the structural integrity of composite materials. In addition to his accomplishments with terahertz imaging systems, he has research interests in photonics, advanced data analysis, inverse problems, robotics, advanced manufacturing, and system modeling and simulation. Applying terahertz imaging to works of art, Albert led a team that discovered the signature of Master Goya in one of his earliest paintings. This year, under supervision of the Strauss Center for Conservation's director, Narayan Kandekar, he has taken part in research at the Harvard Art Museum. Albert received his Ph.D. in applied physics from the University of Barcelona in 2004 and an MBA from Rensselaer Polytechnic Institute in 2008. He has had numerous publications, several patent disclosures, and is a frequent speaker in specialized conferences and workshops. Please help me to welcome Albert Redo-Sanchez.
So following with the words of Francesca, one of the things interesting in my case is I don't come from the art field. So my background is kind of strongly based on applied physics. And at some point a few years ago, I realized what I was doing for industrial applications could have an application for art. And also I had an personal interest in art. So that's why I kind of began poking, exploring the possibilities of terahertz in art, and did some collaborations with my colleagues in Barcelona. And again, it's very important in that case, especially in my case, I don't have a background to collaborate with people in the field, and that has been critical. And everything that I'm going to show here, it's just, I'm still doing the research on these images. So actually, yesterday I was discussing with the research staff at the museum, at the Harvard Museum here, some of the results that I'm going to show here. So what I'm trying to say is that what I'm going to show is kind of almost out of the oven right now. So it's very, very recent. So some of the things I'm going to say, they are still under investigation. So, but I want just to show you what the potential of terahertz, right? And yeah, basically the title of my talk will be how we can solve mysteries, right? So when you look at art, you can also look at art from emotional perspective, but you also can wonder what the artist was thinking when he was painting that piece, or what was the reason for the piece to be the way it is. So my idea was, okay, how we can use technology to kind of get an insight on these thoughts, right? And I want to start with an example. That's an example that I've been scanning this August at the Harvard Museum. And in this example, you look at this painting and you think, well, it's a nice painting. And one thing that we fail sometimes to realize is that we think that the painter originally had this idea in mind when he painted this. So what we see is the end result of that process. But we sometimes forget that before, the painter may have doing different trials. Maybe the painter have showed different versions of that painting. So the idea is maybe we can use technology to have an insight on idea of maybe how those old versions look like before the final product, right? And if you look at the X-ray, which is one of the tools that is available, well, you get the X-ray image, and you see a lot of interesting features. You can see, let's see, you can see the structure of the frame, right? And then you also see kind of you can guess the figures in the painting, but they look like ghosts, and in some of cases they don't match exactly what you see optically. So that's kind of interesting. Let's say here's another example of wrestling with mystery. So if you look at this scene over here in the visible, you say, well, that's a nice scene in the painting. But if you look carefully in the X-ray, you can kind of analyze. You can see, for instance, if you focus on this area, the arms were positioned differently. The legs also were put a different way. So the heads maybe will be different. The hands also different. So So you can kind of realize that, yeah, the painter was kind of toying with maybe the final scene, and maybe had some difficulties in one of the compositions. So he decided, well, that doesn't look very good. I want to try different approach. So that's one of the. So the idea is with multispectral imaging that you can get the images at different parts of the spectrum, and try to come up with all these pieces of information that can give you an insight of the process of the creation of that piece. Here's another mystery that we just were discussing yesterday with the folks at Harvard Museum. And if we focus on the head, in that case, we have the visible, we have the infrared, we have the UV, we have the X-ray, and now we have the terahertz, which is the part of the spectrum that I want to introduce to you. So far, I think X-ray, UV, and infrared are kind of well-known techniques in art inspection, but I want just to introduce you that terahertz could be another complementary region of the spectrum that you can get a lot of information from that area. That could be interesting. And yeah, what's the mystery here? The mystery that we were discussing is that if you look at the X-ray image and the terahertz, it seems that the head at some point was bigger than actually it is. So, and I'm going to show you some of the evidence that that's the case, and that kind of makes wonder why decided to paint the head smaller, or why he tried a bigger head, and there are other features that are interesting. So this is an example of if you overlay the UV with the optical. Well, in the UV there are some features that can give you some information about maybe degradation, some chemical change in the painting. And for instance, there is a feature if you look at the face of the chin, going back to UV. So let's pay attention here. You see some feature going along, right? So you see this feature here, these kind of bright spots. And again, here's where sharing this data with a conservationist makes sense, because I don't have background to interpret that information. So I can tell you, okay, there is something here, take a look at it, and then maybe decide what's going on there, right? But that's just to give an idea that if you use other parts of the spectrum, you can get information about that piece that you don't see optically, right? So optically it seems a very nice head, but there is something going on there. Here it's the same overlay, but it's not the same. It's the overlay of optical with X-ray, and the X-ray image looks very faint. So there is some structure, but not very clear. So it's not. The contrast is very low, and that's one of the problems of X-ray in this particular field. Contrast normally it's very low, so you kind of have a sense what's going on, but you don't have a high contrast. So you really have to guess a lot. But here I want to just point out, if you look at the chin and this feature over here, and also some feature over here, that you can kind of guess that the hair at some point, the head was bigger because of the hairline over here. Seems that was bigger, and also the face, if you look at the region at the front of the face, and also the chin. So it seems that the head at some point was bigger. But again, the X-ray image kind of leads you in that direction, but the contrast is not very strong. So what happens if we take the same area in terahertz? And this is what happens. So this is the image in terahertz. And here, again, if you just follow this area, you have a much stronger contrast. So that what you see in X-ray. So basically, terahertz provides a higher contrast X-ray version, and you see some features here that kind of leads to think that the head was bigger, and also the face over here seems to be a little bigger. And an interesting point that we were discussing yesterday is the feature around the ear. So if you look at the hairline here, so at some point, you see, at some point the ear was completely uncovered. But later on, he decided to cover this part of the ear. So, I mean, that's it's kind of interesting, right? And another feature is the ear canal. So you have three features here that can be the ear canal at some point. So the orientation of the ear could be different from the final product, from the final version, right? Which is here. So we have these features. We have the The hairline is different. So, and again, that's something that we were discussing yesterday with the staff at the museum, at the Harvard Museum, and we still have to figure out why this is, or what's the reason for that. But at least we have a piece of evidence that definitely at some point that ear looked different, and maybe the head was bigger, and maybe it was even looking at the different orientation, right? So that's something that only Terahertz in that case can provide this piece of information. Right? So I give you these examples of what multispectral imaging is, but just kind of to give you a message, what multispectral imaging is basically combining images acquired at different parts of the spectrum and get all these images some kind of consistent information. And here is basically the electromagnetic spectrum from microwaves to X-ray. And so far, the visible is kind of the primary region that we work with because our eyes are working in the visible, so that's we tend to develop tools in that traditionally, that's the region that we have worked the most. And again, we have ultraviolet, X-ray, and also infrared, but then it's the terahertz part that I want to make you aware that now it's available also for these particular applications. And the idea is that to combine all these parts of the electromagnetic spectrum with the goal to get a structural and chemical data from your sample. So you just not only can see the composition of what the final scene is, but you can understand the materials that are made of, whether the structural condition of the painting it's good, or maybe it has some defects or has some problems. So that's kind of the idea of using multispectral imaging. So to combine all these parts into one set of data that kind of provides a comprehensive understanding of your sample. And here I leave microwaves, but I don't include microwaves because microwaves is just, I want just to point out the terahertz between microwaves and infrared, so just the people have an idea where this region lays in terms of the electromagnetic spectrum. But microwaves is not very useful for this particular case because resolution is not very good. Microwaves, the wavelength is in the order of centimeters, so it really doesn't provide enough spatial resolution for most of cases. So normally that's a tool that could be interesting from a structural application, from a structural studies, but not maybe to resolve fine details. So I've been talking about terahertz, and I just want to try to convince you that this is an interesting tool for art inspection, and I think there are 4 reasons that this is the case. One is because it's kind of similar to microwaves. It can penetrate most materials. So you have this capability to penetrate very deep into materials like plastic, cardboard, paper, ceramics, all these kind of dielectric materials are normally fairly transparent to terahertz. So you have a good chance to go very deep into a sample. The other feature, it's because the wavelength is shorter than the microwave, so you have sub-millimeter resolution. So you can resolve very fine details in your object. So maybe in the order of millimeters, a millimeter depends on your optical configuration, so you can have very nice images. It's a non-contact technique, so which is kind of ideal. So you don't want to touch your object so as little as possible, right? So in that case, it's ideal. And one particular thing, very interesting, is provide what we call time-of-flight data. Time-of-flight data refers to the fact that you can have depth information. So it's like a radar or not like an ultrasound. And that's how I like to call it to terahertz. Terahertz is kind of electromagnetic ultrasound, which is not scientifically correct because it's kind of but I mean, I think it's a good way to give people an idea what the terahertz is. And basically, it's like an ultrasound in the sense that the terahertz system works by generating a pulse, sending that pulse to the sample, and then the sample, if it has different layers, each layer is going to generate an echo that's going to reflect back to the system. So basically what we do with the terahertz system is collect those echoes in time, and then the separation in time is related to the depth of that layer. So that allows you to measure the position of the layer, the thickness of that layer, and if the layer has different reflectivity, it has a distribution of reflectivities because the index of refraction can change locally. So then the amplitude of that pulse is also going to be different. So you can map this change and generate an image of that particular layer. This is one of the foundations also. Some application I'm trying to develop is this reading through a book application. So that's also something that it's based on the same principle and kind of can be applied for that. So here again, it's kind of summarizing the strengths and weaknesses of each part of the multispectral tools that we have. And starting from the shortest wavelength to the longest wavelength, we have the X-ray. And again, X-ray, the benefits of X-ray, it has the highest penetration, the highest resolution, but X-ray doesn't provide depth information. The normal X-ray, there is the phase contrast X-ray that can provide some depth, but that's the kind of a technique that is being developed, and it requires a synchrotron, so it's not a very practical technique. And also X-ray, it's hazardous for humans, so you have to be careful with this technique. Then you have ultraviolet, which is an excellent, very good technique for chemical analysis of your painting, but doesn't provide also depth information. So maybe you can use kind of OCT techniques, but it doesn't per se provide depth information. And I think I've been told that if you use UV, you have to be careful because it can alter the composition of your piece, so you cannot abuse UV in some of the cases. Then you have, of course, the visible, right? The visible is the main region that we work, and it provides the most rich color and feature images. You can also use OCT to get some depth information, but that's very limited, so the things that you can get, it's kind of limited. And so it basically provides very shallow information of your sample. And the same way for infrared. Infrared has a better penetration than visible, but still it's very shallow compared to what terahertz can do. Terahertz can go millimeters or even centimeters, depending on the sample, into the material. And it provides very easily this depth information, so you can generate these cross sections and analyze the structure of your sample layer by layer. And as I was saying, microwaves, they just have virtues to kind of put terahertz between the microwaves and the infrared, but it doesn't have many uses in art inspection at this point. So here's an example. I talk about that I started terahertz applying terahertz with my colleagues in Barcelona, and this is one of the first applications that we did in this painting from Goya. And we knew that painting was from Goya because we had the history of that painting, who owned the painting and when, so we could trace back to the original, so we knew it was original. But if you look at the painting, there is nothing really that can tell you besides the materials, besides the style, that kind of, you can tell, okay, this is a Goya. But if you look at something here, and this, I'm trying to convince you that this is very similar to one of the signatures of the Goya at that time. So maybe it's not complete, but you can see the Y and A, and maybe the G, right? So the O is kind of missing, but I mean, it's not perfect match, but I hope there is enough resemblance that you have a strong evidence that there is a signature there that you don't see optically because it's covered by a varnish that became dark over time. And so the only way that you can see this feature is using terahertz. So X-ray doesn't show anything because it doesn't provide enough contrast. Infrared cannot penetrate to the position where this feature is, and optical you don't see it also. So that's one of the first works in terahertz and that particular field. So so I was told also to kind of provide an insight of the kind of future, how I see the future in terms of technology, not just terahertz. Maybe terahertz is a part of it, but including all other parts of the electromagnetic spectrum. And the future I like to say we maybe have a city for curators. So imagine that you have a computer with you, and then you're looking at the painting, and then you can talk to Siri, and then you can discuss with Siri what this painting is about. And the idea is that basically what we have so far, this is kind of the human side, right? So when you look at paintings, at the end, all these images come to humans, and it's the work of humans to interpret those images, right? So I was saying that the image I show you in terahertz about this hairline and the ear canals, at some point we have to discuss with the expert in that painting to give a meaning of that data, right? And that's something that it's a human endeavor, right? So we have to understand the artist, we have to understand the technique, and then at some point we have to come up with an explanation of why that was. But the computer is not going to tell us that, right? But maybe we can use these inputs to computers and develop new integrated sensors that can integrate all these channels, and also maybe incorporate advanced computer image processing and also these new thing about deep learning that can provide some direction or some guidance to the curator, saying, okay, look at this position in the painting. That could be something interesting to look at, right? Rather than me try to look at those paintings for hours and try to figure out what could be interesting and not interesting, maybe there could be a computer saying, okay, this region over here is interesting, so just pay more attention here. This region here is not that interesting because it's something that I already know is not interesting, right? So don't pay that attention. So it can kind of help navigate the curator in terms of analyzing the results much faster than just having all the images from scratch and then say, okay, well, now let's start. Right? So it can provide kind of some starting points that can make the research faster. So I want to kind of finish, okay, what's the deal, right? How big was the head supposed to be? So again, that's something I don't know. That's something is to be continued, and hopefully at this point I'm not going to make any declaration of how big the head has to be, but I will be happy to take questions from the audience. So that's it.
From photography to paintings, and we heard about the different methodology, multispectral imaging. So learning more about objects with studying images taken at different wavelengths. And I think what was also really important was the point that Albert made at the end, that the interpretation of these images is really a collaborative effort. So that's when you bring the curator into place, the conservator into place, and look at these images together.